Okay, so today we'll be going through a technical blog written on Postgres and connection. It is a quite old blog, but the concept discussed in this blog are still relevant today. So I would highly encourage you guys to give it a read yourself. I'll drop the links in the comments. But without further ado, let's dive into the blog and see what it's about. So let's try to start from the starting section of the blog itself because I think it would help set up a good grounding of why to even bother with reading this article at all. So the blog starts with you start building your new project. You've heard good things about Postgres, so you choose it as your database. As advertised, it proves to be satisfying tool and progress is good. You put your project into production for the first time, and like you would hope, things go smoothly as Postgres turns out to be well suited for production use as well. The first few months go well, and traffic continues to ramp up when suddenly a big spike of failures appears. You dig into the cause and see that your application is failing to open database connections. You find this chilling artifact littered throughout your logs. Fatal remaining connection slots are reserved for non replication superuser connections. This is one of the first major operational problems that new users are likely to encounter with Postgres, and one that might prove to be frustratingly persistent. Like the error suggests, the database is indicating that its total number of connection slots are limited and that the limit has been reached. Okay, so I hope that helps set up a good starting point on why this might be important to you. Like, if you have been a serious developer for at least 1 or 2 years, you most probably would have encountered such an error regarding database connection or some variant of this fatal error. And on the first look, it might seem that, okay, so this is simply a limit reached error, so let's just increase the limit and it will be solved, right? Well, it's not that simple. And to prove it, let's directly jump to the final benchmarks shared by the author. Over here, you can see that as you try to increase the maximum number of connections that can be handled by a Postgres instance, your performance starts to degrade quite significantly. So, simply increasing the number of maximum connections limit isn't the solution. So, what is? Now, that's a good question. And for that, we'll have to take a little bit deeper look into how Postgres actually works. So let's switch to our diagram and assume this scenario. So you can imagine this as a high level Postgres view where you can see a client is trying to make a new connection, and that connection request goes to its element called postmaster. Postmaster actually forks a new process and creates a dedicated background process to handle any kind of request coming from the client. So it's a dedicated connection created solely to meet any operation requirements from the client. So similarly, you can assume multiple clients requesting for multiple requests end up creating multiple processes. But as you see, these processes aren't really independent. As you can see, all three are trying to reference a global shared state, and that shared state could compromise of various details like all the processes running at the moment, all the transactions ongoing at the moment, and many other such details. So Postgres actually needs to keep track of or even need to have answers for things like which transactions are currently running, which transaction IDs are active, what transaction started before me, and it might not be that apparent at the moment why does Postgres need to keep track of all these things. But why does Postgres needs to know all of this stuff? That's a good question. So to understand that, let's try to look at some examples. Let's say you have two transactions, A and B, both trying to read and update some data. So while transaction A is trying to read the data, say a balance value from a user's table, and you can see that the user table has the balance of 100 at the start, but at the same time, second transaction B is also running and it tries to update the balance to 200 and commit. Now, when we go further down, transaction A wants to read the balance again, but now the question becomes what value should transaction A see? And that actually ends up leading to another concept called isolation scope. So what actually happens is when the transaction B tries to update the value and commit it, as soon as it tries to commit, Postgres actually create two versions of the same value. So by default, the isolation scope in Postgres is set to be read committed. That is, any transaction trying to read any value would always get the latest committed value for that row. So by default, the transaction A would be able to see the 200 value, which is the version 2. But say if the transaction had the isolation scope as repeatable read, Postgres tries to maintain a isolated snapshot throughout the transaction such that during the entire duration of transaction, the balance fields value is set to read the version 1 of the value. And then there is a third isolation scope called serializable, which is similar to repeatable read, but provides or adds some additional serialization benefits, which we'll talk about soon. But now that you encountered this new concept of Postgres actually maintaining multiple versions, this is actually called as MVCC, which is multi-version concurrency control. We can understand it by breaking the terms itself, like multi-versions refers to Postgres maintaining multiple versions of the row values, and concurrency control actually refers to leveraging those multiple versions to help. So maybe the next question that might come into your head is, how long do we keep these old versions around? So actually, Postgres has an internal worker called auto vacuum, which actually runs a command called vacuum, which together are responsible for cleaning up these old versions. So as soon as there are no more transactions referring to the version 1 of the row, the vacuum cleans up that version and makes that space reusable. So I talked about serializable giving you the isolation scope like repeatable read, but additional to that, it also provides serialization benefits, and it does that through a logic called SSI. Now, what is SSI? So SSI actually stands for Serializable Snapshot Isolation. So the main promise of SSI is concurrent transactions should behave as they ran one after the other in some valid order. So what does that mean? So again, let's take an example. Let's say a user has two accounts, current and saving, both with 600 rupees in them. And we have a business rule that the combined balance must never fall below 500. So say we have the use case of the user wants to withdraw 600 from his account. So the developer logic written over here is that we try to read the balance first and see if we try to deduct the withdrawing amount with the total, it's greater than 500. And if it is, we withdraw it. So let's say we get two transactions at the same time, where in transaction A, the user tries to withdraw 600 from its current account, and in the transaction B, the user tries to withdraw from the savings account. So again, the transaction A tries to query the current values and they get the total as 1200. And so 1200 minus 600 is greater than 500. So it decides to withdraw 600 and then commit it. And since transaction B is also running at the same time, they also check and they see the condition passing. So they also decide to withdraw the 600 and commit. But you see what happened here, right? They both read the same value at the same time and decided it was valid to withdraw the 600 amount. But as you can see, that ended up breaking our business rule, that is, the combined balance must never fall below 500. So this is a common occurrence and it is also known as right skew. So now let's look at how serializable scope helps us with this use case. So let's say transaction A begins and it tries to read the value and it sees that, okay, so the condition is passing, and then it withdraws it and commits it. And at the same time, transaction B also tries to read the values and see that the condition is matching. But due to SSI, it is able to detect that something is wrong, and so it ends up throwing a serialization error, which means the transaction has to be retried. And so when the transaction B retries, it ends up reading the latest value, which would be now 100. And so this would end up turning to be 700 and minus 600, which would be 100, and thus will end up breaking the condition logic. And so this would end up breaking your condition. and the transaction would fail to happen, right? So this is how SSI actually helps in such situations. So I think now it would be pretty clear to you guys that why just increasing the number of solution might not be a good idea to the problem, because as we could see that the connections aren't completely independent and that there are actual global synchronization points where they interact. Like processes just don't end up doing begin, select, and then commit. A process actually has to deal with a lot and manage all the synchronization logic. Like it has to receive the SQL, it has to pass the query, it has to plan the query, it has to get transaction snapshot, it has to inspect the transaction visibility, it has to acquire logs, read rows, modify rows, write to wall, update transaction state, release logs, and then finally end up committing the transaction. Thus, simply increasing the number of connection isn't the right answer. You might successfully allow more connections while simultaneously making all 1,000 connection worse. So the main point of the overall topic was, instead of seeing just more connection means more backend processes and more memory, hence the performance issues. Instead, you should more think like more connection leads to more processes, which leads to more concurrent actors, and hence larger global transaction and process state, more contention around shared structures, more CPU and IO competition, and thus each individual query can become slower. So now how do we solve this? Well, we have ended up discussing a lot of the internal topics and concepts, especially these MVCC and SSI concepts, which are actually not even discussed in the blog itself. And that was my main point, to give you something more to dive into, more than the content shared in the blog. But now, to not increase the video length and complexity even more, I would like to cover all the remaining topics covered in the blog quickly. So now, coming back to how to deal with the situation, the author suggests connection pooling, which is basically maintaining a cache of DB connection. This ends up helping reduce connection creation overhead. It helps enforce deterministic value of system requirements. It helps add some back pressure via queues, and it also helps increasing throughput and concurrency without needing to vertically scale our systems. So here you can see a approximate view of this system. Like we have one Node.js process with multiple HTTP requests coming in, but we have a pool of 10. So all these requests can actually share these pool of 10 DB connections that are maintained. So you can imagine if you have 20 connection requests, the first 1 to 10 can get direct connections, and the remaining 11 to 20 can get queued. So as soon as any one of the connections ends up completing their operation or transaction, the request from the queued pool takes and reuses the same connection to perform and continue their operations. So you are able to maintain a maximum number of connections you would like to allow for a node process to be able to make. And also you are able to reduce the connection overhead by reusing the same connection across different HTTP requests. So another topic that the author ends up discussing about is minimal viable checkout. Like if you consider any HTTP request, it ends up doing multiple things apart from interacting with database, right? Like before database, as soon as the request arrives, you might need to parse it, validate its input, and do other operations. And then like in the between, you might end up using connection to write, read, and commit to database. And then after all that, you might end up building response. So the author is trying to suggest the idea that you should only acquire and use the connection only while you are actually interacting with the database, and release it as soon as you're done with your operations. Similarly, he says like releasing connections around foreign mutations. This also points towards the same idea that you should break your work into smallest units as possible and keep external APIs out of a DB connection or transaction work. So I think I would like to end our discussion with the last section of the blog, which I think makes a very important point, which is earlier or even now, I think frameworks and other packages try and simplify the developer experience, which is bring on abstraction layers And abstractions are good. They try to hide the complexity so that developers feel it easy and quicker to get acquainted with the stuff and get to the building part. But eventually, every developer needs to understand the resources underneath their code. Like, I'm not saying you need to master every internal details of Postgres, but you should understand the limits your application depends on, especially if you aim to take your app to production and to a serious scale. So I think I would like to conclude our video with that. Let me know, how did you guys like it? Was it too deep? Was it too narrow? Let me know in the comments below. Until then, peace.